Hello everyone. Today we are going to see numericals on equation of continuity and motion for flow through pipe and flow through annulus. So we are going to see two numericals on flow through pipe and two numericals on flow through annulus. So first start with flow through annulus. The first question is consider steady state incompressible flow, fully developed flow of Newtonian fluid in an annulus between two concentric cylinders of radii R1 and R2. The inner cylinder move upward with constant velocity v, while the outer cylinder is stationary. The system is closed such that net volumetric flow rate across any cross section is zero. Write the continuity equation in cylindrical coordinates. Simplify for steady incompressible asymmetric flow. Consider that the continuity requires net flow rate across cross section to be zero. Express this condition as Vz of R and state boundary conditions for the velocity field. So let's start with writing continuity equation. So this is our continuity equation in cylindrical coordinates. So now let's analyze the different parameters of the continuity equation. So first one is steady state. If steady state is present, then we can conclude that dp by dt will be 0. Now we have a symmetric flow. So dv theta by d theta would be 0 and incompressible flow which makes rho constant. So this term will also become 0. Now we have a fully developed flow. So dvz by dz will also become 0 and as rho is constant, this whole term will be 0. So now technically this term and this term is 0. So our equation becomes 1 by r d by dr rvr is equal to 0. Now integrating this equation, we get Vr is equal to C by R. Now at center, that is R equals to 0, Vr equals to 0. So we can say that C is equals to 0. Because if C is not 0, then Vr will not be finite. Now flow rate across any cross section is given by Q is equal to integration of R1 by R2 Vr Vz of R 2 by R dr. So for any closed system, this value should be equals to 0 and that is given in question. The boundary conditions for this problem are at R1 Vz is equal to V and at R2 Vz is equals to 0, which is the condition used here. This ends our first question. Now let's move to the second question. The second question states that consider steady and incompressible asymmetric flow of annulus between radii R1 and R2. The fluid is injected radially outward from the inner cylinder with constant velocity, while outer cylinder is impermeable. Write the continuity equation in cylindrical coordinates. Simplify for steady and incompressible axisymmetric flow. Show that 1 by r d by dr rvr is equal to 0. Integrate and obtain the radial velocity for Vr and state the boundary condition required to determine the constant of integration. Now let's move to the solution. So first we will start with assumptions. So the assumptions for the problem are steady state incompressible and symmetric flow and purely radial flow. That is, well, Vr should be function of R only. So now continuity equation is given by this form. This is continuity equation for cylindrical coordinates. Now as per conditions, the steady state implies dp by dt is equal to 0. Asymmetric flow implies dv theta by d theta is equal to 0. Incompressible fluid implies rho is equals to constant and fully developed flow implies dvz by dz equals to 0. Now putting all this in continuity equation, continuity equation, we get 1 by d by dr rvr is equal to 0, which is second sub question of our main question. Now integrating this equation, we get Vr is equal to C by R. Now boundary conditions for this is at R equals to R1, Vr equals to V0. So C will be calculated as V0 into R1. So the Vr equation becomes R1 into V0 by R. And this is equation for our Vr. Now if cylinder is impermeable at R2, Vr at R2 is equal to 0 is not satisfied until there is an axial flow, because the liquid which is being thrown outside should escape somewhere. So this setup in practical implies negligible accumulation unless compensated by an axial motion. Now let's move to the third question. The third question states that consider an incompressible flow of Newtonian fluid in a long circular pipe of radius r. The fluid is either injected or removed from the pipe through its porous wall with constant radial velocity Vr equals to Vw at r equals to r. Assume that axial flow depends only on the radial position, that is Vz is function of r only, and that the pressure gradient dp by dz is constant. The data given for this question is the viscosity of fluid is mu, the radius of pipe is r, and wall velocity is vw. The pressure gradient is given by dp by dz, and this all are the objectives of the question. So this is the first question for the pipe, and let's solve it. So first let's write the continuity equation and simplify it. So the assumptions for the problem is steady state flow, asymmetric flow, Vz is equal to function of r only, that is given in question, and V theta is equal to 0 due to symmetry, and dVz by dz equals to 0 because it's a fully developed flow. Now equation of continuity is given by this equation. Now as steady state is there, dp by dt will go to 0, V theta is 0, so this term will go to 0, and as dv by dz equals to 0, this term will go to 0. The continuity equation will eventually become d by dy rvr equals to 0. Now integrating this, we get vr is equal to c by r. Now putting the boundary condition of at r equals to r, vr is equal to vw, we get the equation of radial velocity as r vw by r. Now let's write z momentum balance. So z momentum balance is given by this whole equation. This is the z momentum balance for cylindrical coordinates. Now the condition states that steady state. So dvz by dz equals to 0. Vr is not equals to 0, so this term will pertain. V theta is equal to 0, so this term will vanish. And dvz by dz equals to 0, so this term will vanish. Now dp by dz will be there. Similarly, vz is not function of theta, so this term will vanish, and vz is not function of z, so this term will also vanish. So the equation will become rho vr dvz by dr equals to minus dpz plus mu 1 by r d by dr of r dvz by dr. Now consider the creeping flow assumption that implies that rho vr dvz by dr is very less than mu d square vz by dr square for low Reynolds number. So we can shift this equation here and then merge these both terms to get the final equation 1 by d by dr rvr dvz by dr equals to 1 by nu bp by dz. Now integrating this equation, we get the velocity profile as 1 by 4 nu dp by dz r square c1 ln r plus c2. So now at r equals to 0, vz should be finite, and if we put r equals to 0, so this term will go to 0 and this term will go to infinity. So if at r equals to 0, this is 0, so c1 should be 0, so that the vz is a finite. So we can conclude that c1 equals to 0. At r equals to r, vz equals to 0. So for putting this condition and solving, we get c2 as minus 1 by 4 nu dp by dz r square. So vz will be 1 by 4 nu dp by dz r square minus r square. Now let's move to our last question. Consider steady state incompressible laminar flow of Newtonian fluid through a long circular pipe of radius r. The flow is driven by constant pressure gradient dp by dz. Assume axisymmetric flow with velocity only in axial direction, that is vz is equal to vz of r. Data fluid viscosity is mu, as the data is same as question, and objective is also same as previous question. So let's start. Now this is z momentum balance in cylindrical coordinates, and let's revisit the condition once. So dvz by dz will be 0 due to steady state. Vr is 0 in this problem, so this term will be 0. V theta is also 0 in this problem, so this term will be 0. Now dvz by dz is 0 due to fully formed flow. Dvz by d theta is 0, and vz is not a function of z. Vz is not function of z, so this term will go to 0, and vz is not function of theta, so this term will also go to 0. So the equation of z momentum balance becomes this: dp by dz plus mu 1 by r d by dr r dvz by dr equals to 0. So now solving this, like rearranging this, we get this final equation. Now let's integrate this equation and get the final value of vz. So same as previous problem, we get c1 equals to 0 due to vz finite condition, that is logical boundary condition, and c2 as 1 by 4 nu dp by dz r square by putting the value of r at r equals to r, vz equals to 0. So the velocity profile, we get velocity profile same as the previous questions. So these are the 4 questions that we discussed today, and that's all for today. Thank you.